Thank you. So my name is Angus Taylor and I'm from Microsoft, and I'll talk about deploying your machine learning models at scale. By deploying machine learning, I'm talking about putting a machine learning model into production. So we want to score data and serve the results to users or other systems. And in production systems for many large-scale business applications, we need these solutions to be scalable so that they can meet the demands of a rising user base. They need to be elastic to cope with seasonal demand and fluctuating demand. They also need to be highly available, and they need to run consistently and reliably. And I'm going to talk about some cloud-based architectures which can achieve these goals. So I'm from Microsoft, and most of the infrastructure that I'll be talking about is on Microsoft Azure. But the principles here would be the same regardless of what platform you're using. So for an outline of this talk is I'll talk about using Docker for R, which I think is a really important technology for deploying machine learning consistently. And then I'll talk about two types of architectures you can use, one for batch inferencing and the other for real-time inferencing. So what is Docker and how can we use it with R? Production applications need to be consistent. To do this, they need to have a consistent R code. They need to have a consistent set of R packages. You need to be using consistent R version, and you also need a consistent set of OS libraries. And production applications also need to be portable, because you're not going to be running these applications on your local machine. You need to be able to transition seamlessly from your development environment to production. You also need to have this application often running on multiple virtual machines to enable scaling. And Docker is a technology that enables you to run your applications seamlessly and consistently across multiple machines. The key component of Docker is a Docker container, and this encompasses everything you need to run your application. If you can get your Docker container to run, it will run anywhere that Docker is installed. And it's a way of guaranteeing that your development environment completely matches your production environment. So the things we'll need to have within our Docker container are the code we want to use to score new data, maybe in a script called score.r. We'll need the R installed. We'll need to install our R packages. We'll need our OS kernel and any OS dependencies, and we might even include the R model object itself. Let's go over some key Docker concepts. So we have what's called a Docker image, and a Docker image defines your Docker containers. So your Docker image will contain everything that your application needs to run. And you can run multiple Docker containers from one image. A Docker image is built from a Dockerfile, and a Dockerfile is just a set of instructions that define your Docker image. So where are these components hosted? Well, your Docker containers will run on your compute, so it's most likely going to be a set of virtual machines. Your Docker images need to be hosted on some image registry. You can use Docker Hub or a private registry, maybe in Azure Container Registry. And your Dockerfile is just a plain text file, and you want to keep that within your Git repository. So this keeps your production code tightly coupled with the definition of your Docker image that you need to run your code. And this is what it looks like to build a Dockerfile for an R application. So it's just a set of instructions that define your environment. And for R-based models, I recommend using Rocker as your base images. So for example, in this code on the right, I'm using Rocker/tidyverse and R version 3.5.1. So this will give you your R installation plus all the tidyverse packages that you might need to run your code. And then I'm installing a package from GitHub, and I'm also installing some extra dependencies just directly from CRAN. And the final thing I'm doing here is adding an entry point to my Docker container. And what this is doing is saying, when the Docker container runs, I'll run this R script, score.r. So one other thing I wanted to talk about was the difficulties of package management with R. So with CRAN, it updates every day and it gives you the latest version of the package on CRAN. And this is a problem when you come back 6 months later and you want to install all your packages and you work out there's some breaking changes. So some recommendations I have for working with this are the packrat package from RStudio. There's also snapshot package, and both of these kind of create a snapshot of the packages you need to deploy your model. You can also use MRAN, which is a daily archive of CRAN, and this allows you to look back to previous versions of CRAN and get a previous previous package version. If you're installing a package from GitHub, you can also reference a particular commit, and this means that whenever you install this package later, it will always use the package version that was at that particular commit. And you can also use Anaconda to do package management for R. And the way I'd recommend to use these are to pin your package versions within your Dockerfile. This means that if you need to come back 6 months later and recreate your Docker image, you can guarantee that you're going to be building your image using the same package versions. Okay, let's talk about some potential architectures you could use for batch inferencing. So the scenario we have here is large-scale compute where, for example, for product sales forecasting, at a retail store, you may need to forecast the sales of thousands of products, and you might want to schedule this operation on a weekly basis. And another challenge is the size of the product range changes over time. So the requirements for this use case is we need something that runs efficiently. We might not have the luxury of being able to run this for days on one machine. It also needs to be scalable so that as maybe the business grows over time, the compute can match that challenge. And of course, another requirement is we're concerned about cost always. So to handle this kind of job, I would recommend using a cluster of virtual machines in the cloud, and one tool you can use is Azure Batch. And with Azure Batch, each virtual machine runs a Docker container which is running your scoring job. So you're parallelizing your entire scoring task over a number of virtual machines. For managing costs, a good thing is that you only pay while these machines are running. When they finish their job, they shut down and you're not being charged. And to manage scalability, these clusters can auto-scale. So if the demands of your job increases, you can just add an extra node to your cluster. Another tool that's useful is Azure Container Instance. And this is serverless compute, so it only exists while the container is running. And this will run a Docker container, and in this scenario, I recommend using this as a kind of master node. And this master node just triggers the scoring jobs across Azure Batch. To do this easily, there's an R package that's really useful called do Azure Parallel. And you can have this installed within your Azure Container Instance, and that will trigger your scoring jobs in parallel on Azure Batch. And this container instance is only charging while it's in existence, while it's running. So this is the overall architecture you could use for batch inferencing. Starting with the Azure Container Instances, that's just triggering multiple parallel scoring jobs across an Azure Batch cluster. And each of these VMs in the batch cluster are running a Docker container, which is actually running the scoring process. Another feature is that each of the nodes in your cluster needs access to the same set of data. So you can use an Azure blob storage to link to all these virtual machines, or you can also mount a file share onto each of these nodes so that each of these nodes have access to the same data. Finally, we might use a Azure Container Registry to host our images, our Docker images. We have two images in this case. One image is the master image, and that includes everything we need to run the ACI, and that will include the do Azure Parallel package. And the other image is the worker image, and this will include any of the ML packages that we're using to score our model, and it will also include the actual scoring script itself. So that's batch inferencing. Let's talk about a different scenario, which is real-time inferencing. An example of this would be if we had a website, a retail website, which serviced product recommendations to the users. And you can potentially have thousands of users coming at any one time. And you might also have highly elastic demand depending on the time of day or the season, for example. And the requirements for this use case are we need something that's highly available and can service requests at very low latency. And we also need something that's elastic, and of course cost is also always a consideration. For this kind of scenario, I would recommend using Kubernetes. And on Azure, we have Azure Kubernetes Service, which is a managed Kubernetes service. And this is it's a highly available containerized deployment of your application, and it serves high levels of HTTP requests at very low latency. It also has load balancing, so as the demand for this application increases or decreasing, it can add nodes, it can add containers to manage that demand. Another useful tool for this is Microsoft Machine Learning Server. And what this does is it hosts your machine learning model as a web service. It will listen to HTTP requests and then make predictions with your scoring code, and it will return the response. On the right here, I have some example code of how you can publish a machine learning model as a web service using the package MRS deploy, which is part of Microsoft Machine Learning Server. An alternative is to use the Plumber package. And this is the kind of architecture we could use for real-time inferencing. So here we have an Azure Kubernetes cluster, and we have input HTTP requests coming in, multiple, maybe many thousands coming in at any one time. And we have this ingress controller layer, which is doing the load balancing across a cluster of nodes. In this example I'm showing here, each of these 4 nodes is running 4 containers. So each container can handle a single request at a time. And the ingress controller is managing the load between these. So as any of these containers come free, the ingress controller can direct traffic to those available containers. So the ingress controller sends the data to the Docker containers, and the Docker containers are scoring that data and returning them, and then the Kubernetes cluster will then return the predictions as an HTTP response. And as before, we have a Docker image that's used to build the Docker containers running on the cluster, hosted in an Azure Container Registry. And this Docker image will contain the model object. If you include the model object within the Docker container itself, that means you don't have to load the model object from disk every time. It also contains the prediction function, which actually scores the data, and it will include Microsoft Machine Learning Server or Plumber to actually host the web service. Okay, so to conclude, I've shown you how you can use Docker to create consistent and portable ML deployments using R. I've also showed you how to use the containerized virtual machine clusters on Azure Batch for batch inferencing. And finally, for real-time inferencing scenarios, I recommend using Kubernetes clusters. Thank you.
All right, we're making great time here. Questions?
So I noticed you using the Rocker tidyverse container. Do you change that somehow to use Microsoft OpenR, or do you just use a default R?
It's really up to you. You use whatever image that meets your needs. In this case, I recommended tidyverse just because that contained all of the packages that I needed to for this particular deployment. But as a rule of thumb, I would suggest using the most lightweight Docker image you can to do your task, because as you add more and more dependencies, the size of your Docker image is going to grow. I think the Docker image that I used in this case ran to just over a gigabyte, but you could probably even reduce that if you slim down some of your dependencies.
All right, we got one more.
Yeah, Rocker maintainer here. It's good to see that, but you double pressed the one point. So the reason these tidyverse or version containers by Carl became so popular is that they actually pinned between both the R version that he sticks in and the use of the nrun archive dated to the day of that R release. So when you were saying the additional points about, do pacrat or something else, or use mrun, that's in a way already in. And sort of one of the, and it's sort of like Docker containers built on top of Docker containers, and as they get bigger, there's more stuff in there. I think you then added on JSON Lite, and I would have thought that that's already pulled in by tidyverse, but I could be wrong.
You could be correct.
Minor technical comments.
Yeah, good point. So you don't want to add additional dependencies if they're already included in your base image. Sometimes it can be difficult to know whether something is included in your base image, and obviously there I may have just added something that was already included in the base image. So I think the point with pacrat and snapshot still applies for any additional dependencies that aren't already contained within your base image.